16, 10, 17. Yes, this is part 1 of lab number 5. In part 1 of lab number 5, we are going to test these 4 samples of arithmetic operation, which are multiply, divide and minus, and the fifth one is modulus. Now, what we are going to do is, we are going to assign two inputs, a is equal to 12 and b is equal to 3, and apply these initial 4 arithmetic problems, and on the fifth one we'll use this modulo to check the remainder. Now, coming towards the code, I've already compiled it so that it does not waste time. So here we have initialized our module, declaring all the inputs and the outputs. Here we have declared our 4-bit inputs, which are A and B, 8-bit inputs, which are C, D, E, F and G. Then we are assigning outputs to all our, we are assigning the values to all our outputs. We have C, D, E, F, G. First one has multiply, then divide, plus and minus, and the last one, this line here, it's quite new. 1 colon B1 means simple 1 bit 1, and A is 12, its value is 12 right here, as we have declared it. We'll declare it in the RWF university function. So 12 plus 1 becomes 13, and its modulus with respect to 3, b is equal to 3, b is equal to 3 would become 13 modulo 3, which would become 1. Now we'll quickly jump to running of this. First of all, going to the RTL view. Now this here is the RTL view. What we are doing is we are just simply multiplying, dividing and adding and subtracting. Okay, now coming to its university VWF file, we'll just simply go here, then university program, okay, and go to node finder, list in all, okay, and okay. So here we have all of these numbers. Now what we are going to do is basically assign these the value. Now A equals 12, I'm just changing it to decimal so that it's easier to understand. So its value is 12, its value is 12, we don't want any increment, and okay, its value is 12. Now the second number, its value as an unsigned decimal, I'm giving it just to simplify the whole equation, 0. Okay, now we have our first input as 12, second input as 3. We will set the rest also to unsigned decimal so that we can clearly see from the results what's going on. Now just a second, change all of these to unsigned decimal. Now we will simply compile it. Yes, sure, save, stop. Now what we will get after this is the wave type result, but since I have chose unsigned, so we will simply get our answers. Now here we can see 12 multiplied by 3 equals 36, 12 divided by 3 equals 4, 12 plus 3 equals 15, 12 minus 3 equals 9, and in program we wrote 12 plus 1 modulo of 3, which means 13 modulo of 3. So it will reduce to 1, since 1 is the remainder when we divide 12 by 3. So this was all for the practical implementation of arithmetical operations. That's all for this video. In the next video we will implement the exercise.
Feel buried in the ground, yeah, yeah.
Now coming to next part of our lab, that is logical operators. We will be discussing logical AND, logical OR and logical NOT. Now what these symbols are basically responsible to do are, logical AND will compare two signals, and if any of the given signals is 0, it will evaluate the resultant signal to 0. And for OR signal, if any of the given signal is 1, it will evaluate itself to 1. And for NOT signal, it will be the opposite of signal. If the signal was present, the signal won't be present as a result, and if the signal was not present, at the resultant side signal will be present. Now coming to its implementation, we will be comparing three numbers. One is noun, second one is 0, one is 2, second one is 0, and third one is a 4-bit number that's unknown. Now coming to we know how the noun and 0 are treated, but coming to how unknowns will be treated is, if we are comparing A and C, A is noun, which is a signal that is present, means 1. When 1 is compared with the unknown signal, no matter other signal is present or not, it will evaluate itself to 1. And if this A signal was not present, it would ultimately give unknown, because then the dependency will go on C, on its present and non-presence. Now the dependency has been fulfilled by A, so this will give 1. Now coming to not C, since our signal does not know whether the unknown signal C is present or not, so it won't get that what it's supposed to show, whether it's present or not. Depending on that, it's present, it's supposed to show not present and present, but since it's an ambiguous situation, so it won't show anything, so it would be unknown. Now coming to its implementation on Quartus, I have already compiled the code and there are 0 errors. So first we'll see its RTL view. Come on, man. Okay, so this is the RTL view. DEFDH. Now coming to its university WF file. PST program WF file. Okay, and we'll import all the nodes. Just here. Okay. A B C D E F G H. Now first we'll see our values from our code. What are the values? A equals 2, B equals 0, 4 equals unknown. 2, 0, unknown. 2, 0, unknown. It's 2 in binary, reduce the increment to 0. Now what 2 equals in binary is 1, 0. Okay, and after it, now 2, 0, and this one is unknown. And okay, so now we'll be compiling our code. And save thing. So now this is the result of our code. So here's what it says. Now for D, when we were comparing both the numbers as AND, both the signals were supposed to be 0, but in our case one signal was 0 and one was present. Okay, we can see here, so it would have evaluated itself to 0. Now coming to the next, to see if any of these signal was present, if any of these bits was 1. Yes, this one bit was 1, so it evaluated itself to 1. We can see right here. And after that, coming to the 0, 0 compilation, which was the third one. Third compilation was not of A. Here we can see A signal is present. It has a bit that's active. Hence, it would have reduced its not to all zeros. Here we can see all zeros. None of the signal is present. Now coming to the comparison of A and unknown. So it was supposed to see whether any of the bit in this first part and in this third part is present. So yes, one bit of active 1 is present in A. So it would have evaluated itself to 1. Hence, it's the OR of the noun signal and the unknown signal evaluating itself to 0, 0, 1. The signal is present. Now coming to the final thing, it was supposed to compare whether, let me verify, yeah, it was supposed to give the unknown of C. it was supposed to give the unknown of C. Since this signal here is unknown, so we cannot say what would be the not of C, the opposite of C. Hence this signal has shown X. It was supposed to give 0 if the signal was 1, and it was supposed to give 1 if the signal was 0. But since it's unknown whether the signal is 1 or the signal is 0, so it has evaluated itself to X, which means it does not know what's the result, it's unknown. Hence all these results match the results that were expected. That's all for this logical comparators, the logical operators. Now we will move to the next part of lab.
You're buried in the ground, yeah, yeah.
Okay, continuing our logical operators, what we are going to do is these 4 questions given right here in the form of code. Directly coming to Proteus, I have already run this code. I have compiled it so that it won't waste our time. Quickly explaining it. These are the 4 questions given here. I have assigned each one a separate variable and this wxyz. Now use of these 7 and 4 bit use of this 4-bit numbers for outputs is not necessary. Since for logical operators the output is a single bit, whether the condition is true or it's not, or unknown, that's another thing, X, but it would give us only a single bit. But however we are using 4, so we will just reduce. Since I have already compiled it, I will directly jump to its RTL view. RTL view. This is the RTL view. Nothing clear here. So we will jump to its university VWF file. So here, coming to its university VWF file, I have assigned each of these variables their respective values. These are the inputs we were supposed to give here. If I can show you, it's 67, 0, 1, 1, 2, 0, 1, 1, 1. Same goes here, the values I have assigned, 67, 0, 1, 1, 2, 0, 1, 1, 1, as it was there. So these are the variables that we are going to compare, and these are the outputs we are going to get. Now one more thing, now it's quite difficult to convert each number into binary every time, so what we can do here is directly change it to unsigned number, give it a value here as I have typed 67, and later on with no increment, give it a value like I have typed 67 here. Okay. Now then we will change it to binary, so it will automatically generate its binary number. Now compiling in this part, yes, now these are the results we get for our W, X, Y and Z questions that were given. So they are 0, 0, 1, 1. We can change it to an unsigned number because we only get 0 and 1, just so that it makes a bit more sense. Or we could have reduced it to a single bit as I told earlier. So our results are 0, 0, 1, 1 for the given questions. Now quickly explaining it, first function was not of A. Not of A means if this signal is present, then here we will get 0. Yes, this signal has some bits which are 1, so we got 0. The next part of the question was comparison of 0 and 1. Since AND gives 1 only if both are present, since one of them is not present, which is B, hence here we have got 0. Coming to the next part, the C part was 1 or 2. Since both of these signals are present, the OR function is supposed to give us 1 when any of the signal is present. Here we can see this signal is also present, this signal is also present, both have some bits which are 1, so it automatically gave 1. Now coming to the next part, the fourth part, here it's the OR of 1 and 1 and not of 1. Okay, so now giving it a 1 and 1, it becomes 1. Okay, and now here not of 1 becomes 0, but 1 and 1 becomes 1 and 0. Now from all these bits we are comparing 0, 1 and 0, 0 or 1 or 0. Okay, and now one bit is 1, so we'll get 1 as a result. So we got here 1 as a result. I hope you are understanding this. Combining these both becomes 1, this becomes 0, not of this becomes 0, but the central bit is 1, so 0 or 1 or 0 becomes 1 here. Let's note down the results, and that's all for this part of the video. We'll skip to the E part, which is a separate program, which is the gamma module. That's all for this video. We'll go to the next part.
Feel buried in the ground, yeah, yeah.
Now coming to the E part of our question of logical operators, here we are supposed to give our input beta a value, 1 bit value 0 as an input, and alpha will get the value of naught of our input, which means it will get naught of 0, which means 1. And here we are supposed to compare this output right here and this 0, which means we are supposed to make an OR of 0 and 1, hence 0 or 1. It's testing on Quartus. I have written down the code, I have compiled it, so I will directly jump to the part of its university program. Okay, node finder is all. Okay, so now we have only one input, just rearranging it. So it has value of 0, and we are supposed to run it and see what will be the value of alpha and gamma. Yes, save. Now here is what we are getting. So our input is 0, and not alpha was supposed to get naught of our input, which becomes 1. Okay, and after that we have OR of this 0 and 1. OR of 0 and 1 is 1, hence both these results are okay for our alpha 2 and gamma, and value of gamma is required in the question is 1, as we can see right here. So that's all for this part. We'll move to the next part.
Feel buried in the ground, yeah, yeah.
Coming to next part of our lab, which is relational operators. Now relational operators are less than, equal to, less than, equal to, greater than, or and greater than, equal to. Now how these operate are, these can give only two results, whether the our given condition is true or our given condition is not true, 1 or 0, and the third case is unknown, which is x. Okay, now what 4 numbers, 3 are known, 2, 5 and 2, a, b and c, and fourth one unknown 4-bit number xxxx. Now what we will be seeing here is whether 2 is less than 5, 2 is less than 5 or not, whether 2 is greater than 5 or not, whether 2 is greater than equal to 2 or not, and whether the unknown number is less than equal to the known number a. Now coming to its implementation on Proteus, I have copied the same code. Now coming to its implementation, as just let it compile. Okay, now as you can see there are no errors, only warnings. Going to the new university VWF program file. Okay, and insert nodal bus, node finder, list all. Okay, and okay, so 1 A B C D E F G and H. We have our 4 outputs, 4 inputs. Let's verify it with the code. Okay, coming to the code, we have A, B, C and D, which we are going to assign 2, 5, 2 and xxxx, and we'll get 4 outputs. So these are total of 8, 4 inputs and 4 outputs, assigning them values 2, 5, 2 and x, right? 2, 5, 2 and x. Yes. 0 0 0 10 equals 2 in binary. 2 and next is 5. 4 plus 1 equals 5. 0 1 0 1, reducing to 0 and giving it 2. Okay, this is supposed to be an unknown number, so we will simply write x x x x. This is 0. Okay, now compiling this code, get our results. Save. Okay, now seeing the results, what we have here is whether 2 is greater than 5. Yes, 2 is greater than 5. It says 1, which means 2 is greater than 5. The second part, whether 2 is less than 5. It says 1. Yes, 2 is less than 5, and hence our condition is true. Coming to the next part, whether 2 is greater than 5. No, 2 is not greater than 5. It gives 0, which means 2 is not greater than 5, falsifying our situation. Now coming to the next part, whether 2 is less than equal to 2. 2 is less than equal to 2 or greater than equal to 2. Yes, whether 2 is less number is less than equal to 2 or not. Yes, 2 is not less than, but it's equal to 2, hence 1. Now coming to the next part, where we are comparing whether the unknown number, this unknown number is less than or equal to the known number a. Now since we don't know the number we are comparing, so we will get an unknown output, which is x. Hence all these results are just according to what we were supposed to get. Like here we should get 1 0 1 and x, and what we have got is 1 0 1 and x. So that's all for this part of the video. Now going to the next part of the video.
Feel buried in the ground, yeah, yeah.
Moving to the next part of lab, we have 4 operators, which is logical equality, logical inequality, case equality and case inequality. Now what's the difference is, in logical equality, if we get any unknown at the higher parity bit, it will give us the resultant as unknown, saying that I cannot answer it because the higher parity bit of one of the numbers to be compared is unknown. Whether for the case equality and case inequality, it will check the next bits anyways, comparing that whether even if the x were known as 1 or 0, will it be able to give us our answer. So now coming to the example, it will make it more clear. Now we will be implementing these 5 functions in our code. For first, we are saying that a is equal to b. Now we will check it. A is 4 and b is 7. It cannot be equal, so 0. Now next part is c is not equal to d. C here is not equal to d. C is not equal to d because this x is unknown, and so we cannot confirm that if it's 0, yes, it can be equal, and if it's not, it cannot be equal. So what it will give is x. I cannot tell you whether it's 0, whether it's true or not. So that's the limitation of logical equality and logical inequality. Now coming to the next part, we'll be comparing c and f as not equal to. Now comparing c and f, here comparing c and f as not equal to, c is 0 1 0 and f is 0 1. Hence even if these x were known, they are 1 1 or 0 0, this last bit of 1 0 and 0 1 cannot match. Hence it says they can never be equal even if the x bits are known. Now coming to the next part of case equality, d and e. Now matching this d and e, our last bit is 1 0 here and our last bit is 0 1 here. So even if this bit is unknown, even if it's turned 1 or 0, and even this unknown bits turned to 0 or 1, these two numbers can never be equal. Hence it shows the result that no, these numbers can never be equal, hence 0. Now coming to the next part, where we will be comparing c as not case equality D. So here's C as 0 1 0 and our D as x 1 0. Now it will skip the lower parts, it will skip these parts 0 and 1, neglecting these, and move to the next parts that are noun. Hence it gives us 1 because the noun bits are equal to each other. Now moving to its waveform part, which I have already implemented, is showing the same results. Now what we have here is 4 7 0 1 0 x 1 0 x 1 1 and x x 1. Now the results are 0 x 1 1. So as I have already explained, quickly going through it again, it cannot be explained here that likely as I was explaining back there because the numbers are written here. So I have already explained the whole thing, how this case equality and case inequality works. I hope this explains the whole answer. Now moving to the next part of lab.
Feel buried in the ground, yeah, yeah.
Okay, now moving to the next part, which is exercise of the equality part we did just now. I've written down the code. Here I have directly assigned these outputs, these 4-bit outputs, their respective values, and I have compiled their waveform, and what I got as a result is 1 1 x x. And coming to its explanation, how is this feasible? So now first of all we are comparing this. Now these two bits are not equal, since this is 1 and this is 0. Okay, now coming to the next, equal to, this is also equal to 0 0 0 0 1 and this is also equal to 0 0 1, hence both of these bits are equal. Now coming to the next part, whether these two are equal. This last bit is unknown, but here we can see 101x and here we can see 101x. Now these bits could be 0, could be 1. Now we cannot define that whether these bits are equal or not, hence the result is unknown. Now coming to the case equality, 101x and 101x. Still these two bits, when compared, even according to their parity, since they have the same significance in their numbers, it will still be unknown. Hence the result that is here in the output, here 11xx, is justified just according to what we were supposed to get. So we will just write the results here. 1 GG. I will write the results later on, but these were the results, and that's all for this part. I'm moving to the next part.
Feel buried in the ground, yeah, yeah.
Okay, now quickly coming to the next part of the lab, since we are running out of time. Here we have these symbols as NOT, AND, OR, XOR, XNOT. Now what is the difference between these and previous is, it's supposed to compare each parity bit with their respective significance, like fourth parity bit with fourth, third with third, fourth with second, and first with first. Now to demonstrate this, we are going to run this test, and I have already written this in Quartus, already compiled it. You can see here I have 0 errors. Now moving to its waveform, here I have assigned the values that was given in the question, 1100, which is 1100, 0011 and 0101. It's not 1100 because it's binary. And now we will simply compile it. Okay, here we have got our results. Now I will be defining each of the result. So the first result is for NOT of A. It was 1100, so every bit was supposed to be reverted. It was 1100, and now what we have got here is 0011. Hence every bit has been opposed. Now coming to the next part, which is A and C. This is A and C. Now what it's supposed to compare is, it's supposed to give 1 only when both the bits of A and C is 1. We can see here its second bit is 1 and its second bit is also 1. Rest of the bits are different, hence only the second bit is 1 and the rest bits are 0. Now coming to the next part, which is A or B. Now we can OR is supposed to give 1 when any of the inputs is high. Now we can see here the first two inputs are high for A and the last two inputs are high for B. Now matching these two, we can get the high inputs at all of these because we are comparing A and B bitwise. Now coming to the next part, which is B XOR C. It gives 0, 1, 1, 0. Now what XOR does is XOR gives 1 only if either of the inputs is 1. Only single input is 1. Now we can see here for the first and the last, we have both the inputs as zeros and 1. Hence we won't get 1 here. But here we have only one of the inputs from the number in the second and third bit as 1 or 0. Hence we got here 0, 1, 1, 0. Now coming to the next part, which is XNOR of A and C. XNOR of A and C. Now what XNOR is supposed to do, it gives 1 only if both the bits are 1 or both. Here we have first bit as 1 and first bit as 0, hence they don't match. And the last bit is 0 and the last bit is 1, they don't match. But in the second bit it's 1 and it's also 1. In third bit it's 0 and it's all. Hence we can say that the second and third bits were matching. So we got 0, 1, 1, 0. Hence all the results given here are justified from the respective bitwise gates applied. That's all for this part. Now we will move to the next part.
Feel buried in the ground, yeah, yeah.
Okay, now coming to the next part of the lab, we will be demonstrating the bitwise exercise. Now what we will be doing is we will be taking the NOT of this 2-bit number, XOR of these two 4-bit numbers, and OR of this 4-bit and 1-bit number. Now coming to its implementation on Quartus, I have already written down the code here. You can see I have compiled it. There are 0 errors. And now coming to its waveform, here I am assigning it values. So our A value is 01, B value is 1010, third value is 0010, fourth value is unknown, which is XXXX, and our E value is supposed to be 1. Our E value is supposed to be 1 with count of 0. Why is increment not? Okay, it's supposed to be 1, but anyways, let me check out in unsigned terms. It still won't allow me to edit here. Okay, let me move it a bit higher. Change its block. Yeah, it won't. I don't know. It's some sort of problem with this program or something. When there is a 1 bit, it won't allow you to edit. It's a restriction in this program. Okay, now we will be compiling this part of the program. Compile. Do you want to save your changes? Yes. Save. Okay, now coming to this. Okay, now our first part. For our first part, we have NOT of. For our first part, which is J. If I can show you here, it's supposed to be IJK. I will rearrange it. IJK. Okay, now this is NOT of A. NOT of A. Here you can see it's 0, 1, and it's opposed to 1, 0. 0, 1 change to 1, 0. Now the next part is we will be taking the XNOR of two numbers, which is B and C. B and C. Now here we can see that all the bits match, only the first bit 1 and 0. These two bits of these two numbers are different, and this is supposed to respond only when the bits are different, so it becomes 1, 0, 0, 0. All of these are same, this different, and this is 1, 0, 0, 0. Now coming to the last part, which is the OR of the unknown number and D. The OR of unknown number and D. So we can see here it's X, X, 1. Why? Because comparing this, the last bit is 1 and OR of anything, whether it's 0 or 1, will become 1. But the initial 3 bits right here won't give us any result until they are null, because these for this they are 0. So it's dependent on these x, hence these 3 bits become x, and the last bit, which is dependent on the second one, becomes 1 because there is 1 already present right here. So our result becomes x, 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 1. Hence these are the results for our exercise. Now moving to the next part.
Feel buried in the ground, yeah, yeah.
Here we have these AND, not AND, OR, not OR, XOR, XNOR, and XAND. So what these do are basically, if all the bits of the number are same, not same, different, matching, they are supposed to give these results by matching all the bits of the same number. So here, if I try to demonstrate and explain, it starts from the left hand side and moves to the left, starting from this side and moving to left. Okay, so now for example, we are going to perform AND of A. 1 and 1 equals 1, again 1 and 1 equals 1, and again 1 and 1 equals 1, 1 and 1 equals 1, and now this 1 and 1 equals 1, again 1 and 1 equals 1. Hence the answer will be 1. Now moving ahead, now I am going to explain OR. So 0 or 1 equals 1, right? Now 0 or 1 equals 1, right? Now 1 or 1 equals 1. Hence the answer will be 1. Now moving to the next part, which is XOR of this part C. Now getting here, 0 and 0 will equal 0. Again 0 and 1 will equal 1. Now 1 and 1 equals 0, because XOR gives 1 only if one of the two inputs is 1. Now since both the inputs are 1, so it will give 0, hence 0. Now coming to its Quartus part, I have already written down the code here. This is the code. Here we have 3 inputs of 4 bit, 3 outputs of 4 bit, and then AND of A, OR of B, and XOR of C. Now moving to its waveform implementation, I have already assigned the values here. Okay, these are the values of A, B, and C, which are 1 1 1 1, 0 1 0 1, and 0 0 1 1. I will compile the results. Okay, now we have got our results, and it says 1 1 and 0, just like I have explained earlier. Since all these are 1, so it's supposed to give 1. Since one of these bits is 1, any one of these bits or more is 1, it gives 1. Now the rightmost 2 bits are 1, and 1 XOR 1 is 0, hence this one gives 0. 0 0 0, 0 1 1, and 1 1 0 here. So all these 3 results are verified just as I explained earlier. Now moving to the exercise of these operators.
Feel buried in the ground, yeah, yeah.
So coming to next part of this lab, of these reduction operators to reduce this 2-bit number using AND, then reduce this 4-bit number using OR, and then reduce this 4-bit number using XOR. Now coming towards its Quartus code, I have already compiled it, and you can see here it has 0 errors. The same code, 2-bit number, 1 2-bit number, 2 4-bit numbers, 1 2-bit output, and 2 4-bit outputs. Now moving on to the next step, opening its waveform file. I have already assigned it values as were defined in the question, 10101x and 1101. Now I will simply compile these waveforms. Now here we have got our results. Now in first function we were supposed to take AND of 1 and 0. AND of 1 and 0 is 0. In next function we are supposed to take OR of this function 1 0 1 x. 1 and 0 is 1, 1 and 1 is 1, and 1 and any number whether it's 0 or it's 1 is still 1. So here we have got 1. Now coming to the next step, which is XOR of this number. So 1 and 1 is 0, and 0 and 0 is 0, and 0 and 1 is 1. 1 and 1 is 0, 0 and 0 is 0, and 0. Hence these results here satisfy our equations, and our outputs for the exercise are here. Now moving to the next part of this lab.
Feel buried in the ground, yeah, yeah.
Okay, now moving to the next part of lab, we have shift operators. In shift operators, we can either shift to the right or shift to the left. Now, the side having the less than side is the side to which we shift. Now, this means that number is shifted from this higher to this lower terminal, this way. Now, moving towards its implementation, the number written here, it's either 1 or 2. This defines that by how many bits are we going to shift that we are trying to shift. Now, moving to its implementation on Quartus. I've already written down this code. You can see here this is a 4-bit input and 2 4-bit outputs. First we are going to shift it to the left by 1, and then we are going to shift it to the right by 2. Now moving towards its implementation, I've already written down the number. 1010 is the number we are going to be testing. Let us just compile it to get our final waveform results. Okay, so these are our results. Now let's see. If we shift this to the left by 1, this one is skipped, and hence we have 0 1 0 and added another 0 here to make we are including this part of the number and skipping the first one, and then when we add 0 it becomes 0 1 0 0. Now if we shift this number this side from towards the right and add 2 zeros in the start, because we are shifting to the right by 2, so it becomes 0 0 1 0. Only this 1 0, the initial part of the number, is remaining, and for the rest of the 2 bits we add 2 zeros. Hence this is called shifting of the signal. That's all for this part. Now we will move to its exercise.
Feel buried in the ground, yeah, yeah.
Now we are going to attempt the exercise of shift operators. Now what we are going to do is compare these two 4-bit numbers 0110 and 1100. Once in first case shifted to the right by 1, and in second case shifted to the left by 1, and then we are going to see whether both these numbers are equal or not, whether we get 1 or whether we get 0. Now coming towards its Quartus application. Now here is its implementation. You can see 2 inputs, 4-bit, as we need 1100 and 0110. 2 outputs for the cases we are going to match. And here is the assignment. Here we have shifted B to the right by 1, and here we have shifted B to the left by 1, and we are matching it with A. Coming towards its waveform implementation. Now this is the number on the left side of the equation. This is the number to match, and this second number is the number we are gonna be matching it with, shifted to the right and shifted to the 1. In first case we are going to shift it to the right, and in second case we are going to shift it to the left. Let's just run the compilation to see. Okay, so now these are our results. So seeing this number here 1100, when we shift it to the right by 1, which means we are removing this 0 and we add 0 in the start. then it becomes 0 1 1 0, since we are seeing only first 3 digits, and in the start we are gonna add 0 since we have shifted to the right. So both these numbers 0 1 1 0 and 0 1 1 0 become equal, hence making it 1. But in case we are shifting, in the second case, when we are shifting this to the right, what we are doing is we are considering only these numbers. Considering these numbers, we add 0 here, hence this number becomes 1 0 0 0, 1 0 0 0, and 1 0 0 0 is not equal to 0 1 1 0, hence it gives false 0. So this is all for this exercise. Now we will move to the next operators.
You're buried in the ground, yeah, yeah.
Okay, coming to the next part of this step, we have concatenation. Now what concatenation does is just like the function append we used for strings in C++. Basically it just attaches two numbers filling the bits available. But we are supposed to define that what's the number of bit we are giving it. For example, if we have to fill 4 bits and we have one 5 bit and one 1 bit number, we are supposed to tell our program that what 3, 2 or 1 bit are we choosing from the 5 bits to fill the spaces. Now coming to how we use this is, here we simply use these round and curly brackets. It means that we are appending these two things, curly followed by round, curly followed by round. Now what we are going to do in this demonstration is we are going to append this 2-bit number and this 1-bit number, which is 1 and 0 0. So we will as a result get a 3-bit number. We will get a 3-bit number that would be 1 0 0. Appending this 1 and 0 0, 1 and 0 0, it will be 0. Now 0 1 0 0 1 and our second number A. Now what we are going to do is, since we have large number of bits, we are going to choose which bit to use from 0 1 2 3 4 5. Okay, now here we have written down that we are using bit number 5 to 3, which means we are using 1 0 and 1 from this number. We are using 1 0 and 1 from this number, which means we are using bit number 5 4 and 3 and the A number, which is 1. So it becomes 1 0 1 from this number and 1 from this number, making it 1 0 1 1. Now coming towards its Quartus implementation. Okay, now here we can see we have inputs, 1-bit input, a 2-bit input, and this one a 6-bit input, and our output of 4-bit. Okay, now coming towards its implementation, I have already given these values as 1 0 and 1 0 1 0 0 1. Now we need two outputs, one of 3-bit and one of 4-bit, but I have named both of them 4-bit, so let me just quickly change it. One of 4-bit and one of 3-bit. Simply copy this part, Control C, Control E, and here's the second one, here's the first one. Change its commands to 3-bit. 3 bits. 3 bits means 2 0. Now we will simply recompile it so that we don't get our error. Just fitting the requirement of the question. We close our old WF file. Okay, now here we have got 0 errors and 16 warnings. Warnings are always ignored. Now university program VWF, okay, and here we import all the nodes, list, importing all. Okay, so we are going to give it 1 1. It will stay 0 0, and the last number we have will change to 1 0 1 0 0 1 1 0 1 0 0 1 and increment by 0. And now we will simply run our simulation. Yes, save. So here we have got our results. Now our results are 1 0 0 and 1 0 1 1. They are quite disturbed because of this 1, because we cannot change its increment to 0 for some reason in this program. But combining 1 and 0 0 makes it 1 0 0, and combining these first 3 bits of 1 0 1 and then A makes it 1 0 1 1. Hence this output is depicting the result I have just explained earlier. Now we will move to the next part of this lab.
Feel buried in the ground, yeah, yeah.
Now moving to the next part of the lab, which is replication. Now what replication does basically is it replicates the number of times we tell it to. Here we are telling it to replicate our 1-bit number 1 4 times, hence it becomes 1 1 1 1. It's just like copying a number or repeating the signal the number of times we tell it to. Now we'll go towards its Quartus implementation. I have pre-written the code and compiled it. Here you can see I have 0 errors. Now moving to its waveform implementation. Here I have provided it with 1, and here we will see our result. It's still unknown. I'll compile it. So now here we have our result. When we replicate 1 4 times, it becomes 1 1 1 1. This is just a simple attempt of this lab. Now we will move to the next part, which is the last exercise of this lab 5.
Feel buried in the ground, yeah, yeah.
Assalamu alaikum, this is the last part of lab number 5. I've been working on this lab from 7 hours consecutively, and now coming to this last part of the lab, this is the last exercise number 7. In this exercise, what we are supposed to do is we have 1-bit number, 2-bit number, a 4-bit output and a 10-bit output. Now what we are going to do is we are going to replicate this 1-bit output to make it 4-bit. Here its value is 1, and when it's replicated it will become 1 1 1 1 1, making it a 4-bit 1. And now next we have this input of 2 bits, that's 0 1, 0 1. Now what we will do is we will concatenate this in the start as 0 1, and then with the replicated 1 1 1 1, and then again 0 1, making it 0 1 1 1 1 1 followed by 0 1 0 1, then 4 ones, then 0 and 1, B, C and then B. Now this will make 8 bits, so first 2 bits will be 0 because they are left empty, and our output is a 10-bit number. So now directly moving to its Quartus implementation. Now here I have written down the same code with a little bit of commenting and that stuff. Now we will move to its waveform implementation. I've already given this a value. So our B had a value of 0 1, and our first number A had the value of 1. Now we'll compile it. So we have got our results. It's a bit late, but I discovered this amazing tool here where we can zoom on the part of wave we want to show only 1 bit of 1. Now here what we can see is our first number is 1 and our second number is 0 1. If we zoom out a bit, our second number is 0 1. We'll zoom in here. Okay, our second number is 0 1, and our third number will become 1 1 1 1, because we are repeating the number up here 4 times, but because of its one period that it shows, because of one bit 1, it's showing here 0 0, but we'll focus on this part mainly, this part, the 1 1 1 part when it's high. Now combining this 4 times, it becomes 1 1 1 1, and then combining B in the start, which is 0 and 1, combining B in the start, which is 0 and 1. Here we have this part as B, and then we have 4 ones which are from here, this C part, and then we at last we have B again, which is 0 1, and first 2 bits are left empty because this is a 10-bit number, and even after concatenation we have only 8 bits, but to form the added in the start 2 zeros as the significant bits. That's all for this step. Thank you. Allah Hafiz.
Feel buried in the ground, yeah, yeah.